Hey, if you're gearing up for the AP Physics 1 exam, you are in exactly the right place. We are about to break down a concept that can be a real head-scratcher for a lot of students, the normal force. Specifically, what happens when you put something on a ramp. Trust me, nailing this down is absolutely crucial, so let's get right into it. Okay, right out of the gate, a quick question for you. Take a look at this equation. Normal force equals weight, or N equals mg. Is this always true, or is it false? Just take a second. Got your answer? Okay, good. Hold on to that thought, because we're about to put it to the test. So, to figure out why there's so much confusion, we've got to start where this rule actually seems to make sense, on perfectly flat ground. This is basically ground zero for the myth. When you've got a box just sitting on the floor, the physics is pretty simple, right? Gravity pulls the box down with a force of mg. The floor has to push back up to support it, and that's the normal force, N. Since the box is just sitting there, not crashing through the floor or flying into the air, the forces are balanced. So in this one very specific situation, N does in fact equal mg.
But, physics loves to throw a wrench in the works. What happens when we take that nice flat surface and we give it a little tilt? Well, this is the exact moment where our simple, comfortable little rule completely shatters. And this shows you the problem perfectly. Gravity is stubborn. It always pulls straight down, right towards the center of the Earth. But the normal force has a different job. By definition, it has to be normal to, which is just a fancy way of saying perpendicular to, the surface it's coming from. And you can see it right there. Those two arrows are not pointing in opposite directions anymore. The whole thing is out of whack. So how on earth do we solve this? We can't compare forces that aren't lined up. The solution, and I'm telling you this is the secret to every incline problem you will ever see, is that we have to break the gravity vector into pieces or components that do line up with our new tilted world. This is the big aha moment.
Okay, let's walk through this together because this is the most important skill you're going to learn for this topic. First, you draw your weight, mg, pointing straight down as always. Then, here's the magic trick. You tilt your whole perspective. You literally tilt your x and y axes. The x-axis now runs down the ramp, and the y-axis points straight out of it at a 90-degree angle. Now that we see it this way, we can split that original gravity force into two new parts. One part that's trying to slide the box down the ramp, which is mg sine theta, and another part that's trying to push the box into the ramp, and that one is mg cosine theta. And here is the absolute key to understanding this. The ramp doesn't actually feel the box's full weight. Think about it. Part of gravity's job is now just trying to make the box slide. The surface, the ramp itself, only has to push back against the part of the force that is pushing perpendicularly into it. So this leads us to a much, much better way of thinking about normal force. It's time to get a new definition that's going to work all the time, no matter if you're on flat ground, a steep hill, or even upside down in a loop. Here we go. The normal force is the support force that a surface provides, and it always, always, always acts perpendicular to that surface. It's basically a reactive force. It only pushes back as hard as it needs to against whatever is pushing perpendicularly into it. That single word, perpendicular, is everything. And that brings it all home. Since the normal force's only job is to fight back against that perpendicular push, it has to be equal to the perpendicular component of gravity. And that gives us our new all-powerful formula for inclines, N equals mg cosine theta. So why do we spend all this time on this? Why does it matter so much? Because I promise you, getting the normal force right is the first and most important step for a huge number of problems you're going to face on that AP exam. Let's look at why it's such a big deal. This table really just lays it all out there. At 0 degrees, that's our flat surface, the cosine of 0 is 1. So the normal force is 100% of the weight. Makes sense. But just look at what happens as the ramp gets steeper. At 30 degrees, the surface is only supporting 87% of the weight. By the time you get to a steep 60-degree angle, it's down to just half. And then, the wild one, 90 degrees. That's a vertical wall. The cosine of 90 is 0. The normal force is 0. The wall isn't supporting the object's weight at all. All right, so if you're studying for the exam, these are the points to remember. First, get the idea that N always equals mg out of your head. It's a trap. Second, normal force is always, always perpendicular to the surface. Third, on an incline, your new best friend is the formula N equals mg cos theta.
And finally, and this is the big one, you absolutely cannot calculate friction correctly without the right normal force, because that friction formula, Ff equals mu n, depends entirely on it. If you mess up n, you will mess up friction. Every time.
So, to leave you with a little challenge, think about a roller coaster going through a vertical loop. Using what you now know about normal force, where in that loop do you think the track is pushing on you the hardest? Where is that normal force the greatest? And even more interesting, could there be a spot, maybe at the very top, where it drops all the way down to zero? Chew on that a little bit. Thanks for tuning in.